Here we go. So go to page 823. So when you have molten salt.
At this time, please excuse grades 9 through 12 for career fair at the cafeteria. Thank you.
Sorry, guys. So if you have molten salt, it's easier to understand who's oxidized, who's reduced, than when we have a solution, and this is where we left off. I'll come back to this in a minute. Let's talk about this one first. So if the cathode is negatively charged and the anode is positively charged, and the curriculum says a few times, students do not need to label the charge on the sign on the anode and cathode for electrolytic or galvanic. That's great. But I like to talk about it because the cations always migrate to the cathode, both cells. When you have your two half cells for voltaic, when you have your, let's say the cathode's over here, when this fills up with positive charge and your anions, the anode fills up with negative, and that's the same time equilibrium is reached, the cell stops. It's the same kind of concept here, except this cell won't stop until the battery essentially runs out. So, but it's the same exact concept. The cations go to the cathode. Anions go to the anode. Why is that relevant here? Well, if it's just a molten ionic solid, liquid, the positives always go to the cathode. What does that tell us? If you can remember, cations go to the cathode, that kind of really simplifies this. What happens at the cathode? Oxidation or reduction? Right, anox, red cat. So if you know and can remember, cations go to cathode, anions go to anode, now you know which half reaction is happening over here. It's where the Cl- is losing 2 electrons. I know I wrote it backwards, but again, that's because on page 823, they're all written in the same direction. But sometimes in the cell, it's actually flipped, right? So I'm just writing exactly what you would see on in a chart. That's why I wrote it that way. But technically, this is flipped. Cl- is losing 2 electrons. You're going to see chlorine gas bubbling because that's what's formed. So again, anions go to the anode, so you know Cl- is in that half reaction. Cations go to the cathode, so we know reduction is occurring. Na is gaining an electron and plating itself, trying to, it's a liquid, on that cathode. So another thing to bring up from Regents is the metal plating, electroplating is always at the cathode. When I made those copper plated, whatever it was, keys or, kids give me things, the copper plate, it's always the cathode. So I actually hook the wire directly up to whatever that metal is. A key, I've done bracelets, I've done, I did an iPod once, iPod a long time ago. Anyways, that's where you do the electroplating. Why am I bringing that up? Because that's where the metal goes. Why? Because it's the cation. So I'm just trying to make these connections to help you be able to look at this and make more sense of it. Not just rely on the chart and figuring out, all right, well, this one's a negative number, this one's positive, what does that mean? So really, if you just look at the cell, what's in there, Na plus Cl minus, and try and remember, cations go to the cathode, anions go to the anode. So that half reaction is occurring here, and this half reaction is occurring there. Okay, so when it's just 2 options, that's a lot easier. Over here, it's a different story. So we got to this point yesterday, correct? We labeled these, maybe not exactly like this, but I tried to separate, okay, reduction occurs over here, and my oxidation occurs over here. Here's my 2 options for oxidation. Here's my 2 options for reduction. So this is important that you're really listening here. Inside this, I have 3 species, K+, Br-, and H2O. If they were to give you these 4, like just in a list, like in a box, right next to the question on the AP test, you're going to have to figure out which one is actually happening here and which one's here. So 2 of these, 1 of these is going to happen at this piece of metal, this cathode, and 1 of these is going to happen here. The other one doesn't occur. So the first step is to be able to separate reduction and oxidation, like what are my options. So the way I teach it is, here's a Br-, here's a water, here's a K+, here's a water. Those are the 3 species inside here, right? So you have water. So water is either being reduced or oxidized. You have to figure that out. And potassium is being reduced, and the bromide ion is being oxidized. So we have to figure out what's going on. So again, let me back up here. If you're given these four, how do you know which one's which? Well, Br minus is on one side of the arrow, the electrons are on the other. That means it's oxidation. That means it's losing it. Yes, the arrow is going this way, but remember, they're all written in this direction. Sometimes you have to flip them in your head or maybe even write it down because that's what's actually happening. So technically, this is going the other way if this is the half reaction that's occurring here. So Br minus is losing electrons according to this half reaction. I'm going to say that again. This half reaction is telling me Br minus is losing electrons. Do you understand why? Does anyone want me to explain that fully more, or just again? How do I know looking at this, Br minus is losing electrons? Not gaining. How do I know looking at this, potassium ion is gaining electrons, not losing? This is the whole key. You have to be able to look at these and figure that out, otherwise you can't do this. So who wants to help me out here? How do I know this is a reduction reaction and this is oxidation? And remember, it's with respect to these particles. So how do I know this is oxidation? I mean, I said it, but I want one of you to say it. How do you know, looking at this, this is losing electrons? You gotta work with me here, people. No one knows? Is that what I'm getting? Is that what I'm feeling the energy here? Skylar? Liz? Paige? Ben? Nobody's got anything for me?
With the reduction side, wouldn't it be the K plus? Then I don't. Yeah, wouldn't it be gaining electrons?
So here's what I want you to look at. The Br minus is floating around in here, and forget the water for a second. You got Br minus floating around and K plus. This reaction here shows me, obviously I'm the teacher, that Br minus is losing 2 electrons and turning into Br2. This half reaction, to me, obviously I'm the teacher, it makes way more sense to me. This is gaining an electron, turning into K. That's how I read these. Obviously it's easier for me because this is what I do. You guys need to really, in these problems, and we're going to do another one, look at it from the perspective of the ions and the water. Not from this perspective. No one cares about that. That's not in here. This is. This K is not in here. This is. The water is in here, so we're looking at where's the Br minus and where are the electrons with respect to Br minus. If the electrons are opposite, on the opposite side of the equation, there's no way it's gaining electrons because it's not together. So Br minus is losing these, turning into Br2. The reason I wrote it this way is because that's how you're going to see it. I'm not going to give you the easy way out and write it how it actually looks in here, because that's too easy. The AP test isn't going to do that. They're going to write them all the same way, like in page 823. You have to learn, hopefully today, how to figure out which one's oxidation, which one's reduction. So again, Br minus can't possibly be gaining electrons because the electrons are over here. Now I know what Liz, you were saying, isn't Br gaining electrons? Yes, Br2 is gaining electrons. I'm not talking about Br2, I'm talking about Br minus because that's what's in here. Br minus has to get rid of those 2 electrons to form Br2. This reaction is actually reversed. It's just they're not going to write it reversed. This makes more sense. K plus 1 electron, that's gaining. Right, Leo Gurr, that's reduction. So, instead of asking again and getting more silence, I'm just going to move on. What you need to understand is in the beaker, what species are present, and if they are on the same side as the electrons, they're gaining. That's reduction. If these species are on the opposite side of the electrons, that's losing, that's oxidation. And I really don't want it to come down to memorizing, because then you might get it wrong. I want you to understand it. That's why I'm spending like a few minutes, 5 minutes here talking about this. So Br minus cannot possibly be gaining electrons if there's no electrons on the same side in the equation. If they're opposite, they're losing. If they're the same side, they're gaining. If that helps, great, but I don't want you to memorize it. I want you to understand it. I can't be in your head, but that's how we do these problems. Here it's easy. There's only two options. Obviously this one's gaining and this one's losing. Maybe not so obvious, but it's the same thing. The electrons are opposite Cl minus. So it's losing those. Here it's gaining. So that's really important because otherwise you can't do these problems. You have to separate, okay, these two are reduction and these two are oxidation. Okay, I'm going to move on. Even though I'm not asking for, whether you get it or not. Sorry. Hopefully you do. Now, that's the first hurdle. Once you figure out which, okay, these two are my options for this side, these two are my options for this side. How do I know which one I pick? Because it's only two of these. There's only two half reactions. That's what half means. There's two that makes a whole, right? I can't have two reactions happening at both of them. That doesn't make any sense. Okay. So here's how I'm going to teach it this year. Hopefully it works for you guys. Write this down underneath this problem. Pick the half reaction. And this goes for both sides, oxidation and reduction. Pick the half reaction that is, I'm hoping this is a good way to do it. There's two ways to teach this. I'll try it this way. Pick the half reaction that is closest to zero. And when I say closest to zero, I mean the voltage. So pick the half reaction where the voltage is closest to zero. So, this only makes sense if two things happen. One, they give you the list of the half reactions and their voltage, and guess what? They have to. No one memorizes this stuff. Okay, this number kind of sticks in my head, but that's just because I've been teaching for a while. But I don't have all this stuff. So that's crazy. So the first thing is they're going to give it to you, all four. Second thing that you have to do is what I just spent time talking about. Can you take two of them and say, okay, one of these two is going to be going on over at the anode, and then one of these two is going on at the cathode. So that's the first two steps. Taking what they give you, then separating them. Now, this is the third step. Out of these two, 1.07 and 1.23, who's closer to zero? Out of these two, negative 2.93, negative 0.83, who's closest to zero? I typically like this way better than I actually said a different thing yesterday. I don't know if anyone remembers, and I think I wrote it down over here. There's another way to explain it, and I'll tell you both. The more negative voltage for the anode is the one you pick, and the more positive for the cathode. So out of these two numbers, who's more negative? I mean, that seems so silly or kind of stupid. I would say it's stupid because neither one of them is negative. But who's closer to being a negative? Who's closer to being a positive number? That's another way I've taught it in the past. I like this better because this is actually saying the same thing. So out of these two, and think of like a number scale, right? Or a number scale. So you have like negative 10 to 0 to positive 10, right? Where would these half reactions be? All right, well, we have a 1.07 and a 1.23, right? 1.07, 1.23. Then you have a negative 0.83, and then you have a negative 2.93. So what my little note there says clears this all up. Which of these two is closest to a zero? It's this one. Which of these two is closest to a zero? It's this one. So this is the half reaction that actually occurs. This one never happens. And then this is the half reaction that actually occurs in real life if you were to do this. This one never happens. So this electrolytic cell will never make potassium metal because the water is reduced instead. Why? Because the electron or the reduction potential is closer to zero. And then the same thing here. You're never going to see oxygen bubbles here. Instead, you're going to see bromine because this one is what's oxidized. Why? Because it has a lower voltage, closer to zero. So there's a lot going on, but it's actually, once you get it straight, it's fairly simple. You just have to remember the rules. right? So figure out who's oxidized, who's reduced, so you gotta be able to do that, right? Pick your two options, and then who's closest to 0. Then you can write your balanced equation and you calculate E cell. So I'm gonna stop. Questions? Am I being clear at least, whether you like it or not, or it's hard? I'm being as clear as I can. So I think yesterday, I think I said something backwards by mistake. And we're going to do another one. And the reason it's important is they could ask multiple questions after this, right? So they could ask you the E cell, then what could they ask you? Delta G, then what could they ask you? Okay, then they could talk about thermodynamic, favorability. And there's a lot of things I can't even think of right now. So just the basic, can you figure out the half reactions and get your E cell, right? And then could you even write the overall balanced equation maybe? Well, you'd have no shot if you couldn't at least pick the two, right? You'd have no shot. That would still might be a hard question, but at least you have a shot. All right, so calculate the E cell. Go ahead and do that. What is the E cell for this electrolytic cell? So you know which two we're using. We're using the 1.07 for your anode, and you're using the negative 0.83 for the cathode. And this is easy. It's just a subtraction problem. So it's cathode minus anode. All right, so I'll just do it together here. So negative 0.83 minus 1.07. So you're going to get a negative number, which it should be, because this is not thermodynamically favorable. You're forcing it to happen by using a battery. So what is that? 1.9? Positive 1.9 volts. Negative, sorry. Good catch. Negative. That would create a positive delta G. That would create a really small K. Just reviewing those concepts, right? It's the opposite of everything with the galvanic cell. All right, I'm going to give you one more of these, and then we are going to use the next example. We're going to use it to learn the last thing here. There's no way we're going to get to the lab to talk about it, but that's all right. We'll do it Monday. I would like it. I have no way of really assessing this or grading this, but I'd like it if you could at least read through the lab so you have an idea of what the heck's going on. Like, so you're not coming in and being like, what are we doing? So just look through, just peruse the procedure so you have an idea of what we're doing. And then Monday we'll do the intro activity together, like as a class. Like I'll kind of do it, and then you guys kind of like a demo type thing, and then we'll do the lab. The good news is I'm going to shorten it. There's like a whole guided inquiry, create your own procedure stuff. We're going to kind of do that together just so we can get through the lab. So just for the sake of time, I'm not going to make it as long as I would have. All right, here's what you're going to do. Draw your electrolytic cell, and this time it's going to be salt water, NaClAq. So here's your battery, positive, negative. The negative is your cathode, which is reduced. Positive is anode, which is oxidized. And I have to just cover myself. I always draw it this way. It doesn't mean on the AP test that they may put the cathode over here, they may put the anode over here. So just keep that in mind. Okay? Sometimes kids, especially in regents, they memorize, oh, anode's on the left, and then they don't even try and learn it. They just assume it's always on the left, and then the regents flips it, and they get them all wrong. So don't do that. So you got salt water, Na+, Cl-, and H2O. I'm going to give you a few minutes, but only a few minutes. I want you to try and figure out, based on everything I just went over, which half reaction occurs here and which half reaction occurs here. Okay? I guess I can write them down for you, but you have them on page 823. So they're right there for you. I'll write them over here just to save time. Na plus 1 electron yields Na. That is negative. I want you to write these down though. So don't just take them from the board and do the problem. I want you to write them down. So there's your Na. Cl2 plus 2, and actually I think we have these. We have all these written down anyway from the other problem, but 2Cl minus, that's 1.36 volts, and that's positive. When I do these problems, I always write it positive, even though if you look at 823, okay, it does. It does give you the positive. I feel like there's some AP questions, they don't put a sign at all. So they just write 1.36. I write positive just to make sure I know the difference, just so it's there, it's obvious. It's up to you, that's just my advice. O2 plus 4H plus 4 electrons yields H2H2O, and that's 1.23 volts. And then we got the other one, 2H2O plus 2 electrons yields H2 plus 2OH minus, and that's negative 0.83 volts. So there's your 4 options. So here it is. So they might give you this picture, and they might say, all right, calculate the delta G. And hopefully you're not like, what? You know what to do. You figure out which one's oxidized, reduced, find E cell, and then go from there. Use delta G equals negative NF, negative NFE. So go ahead. Calculate the E cell. And I'm going to use this, like I said, to teach the last thing. Actually, I lied. We'll just leave this alone with the E cell, because if we try and morph this into the last new stuff, it's going to be, be too hard. I'll give you an easier one they wouldn't make you do that anyway. Remember, once you figure out which two are oxidized, which two are reduced, pick the one, so out of the 2 oxidation and 2 reduction, pick the one closer to 0. This one's actually kind of hard.
I don't know if they're going to tell you which one's the anode and which one's the cathode.
They might not. That doesn't matter. It doesn't matter because they're just giving, they might give you the picture just to be nice, they may not. They may just say, the student's performing electrolysis of salt water, given the 4 reduction potentials, calculate the delta G. So they may not even give you a picture, they just may say this is what's happening in lab, they give you these, and all the rules apply. You're still figuring out who's oxidized, who's reduced, closer to 0, find the E cell. So if they do give this to you, then they might actually ask you to draw on it, or they may ask something about the picture, which is why I do go over the signs, because I think it helps, even though it tells me they would never make you label this negative and positive. I just think it helps.
So our cathodes, won't they always have a negative voltage?
Well, it isn't one positive, one negative, like your options. Yeah. Okay, so you're saying that the negative one is always going to be the answer?
Well, no. The negative will be the cathode.
Right. Yeah, that's what I was saying. Yeah. So I'm just going to stick with my closest to 0, because if you do a number scale or whatever the heck that thing's called, I'm drawing a blank there. Isn't that what it's called, a number scale? Yeah. Yes. Okay. All right. Just where do they fall on that scale? The 2 closest to 0. That's what you pick. That's just how I'm going to stick to it. If there's another way you guys want to remember, and that helps you, but that will never fail you. If you can remember that, which of the two is closest to 0, you pick that one. So that's how I'm going to do that. All right, so the oxidation. Oh, do we have an E-cell? Did we get answers? Negative 2.06. Anyone else agree?
Yeah.
So, Tristan, what are the two options for my oxidation here?
Two options are the positive 1.36.
Yeah, so this one, and again, why? Because this is in here and it's losing electrons. So this is one option for oxidation. The other is water. This water is gaining, this one is losing. So here's an oxidation. I don't need to rewrite it actually. And here's my oxidation. So there's my two anode options. So one of those two is occurring over here. These two are reduction because what's in here is Na plus and water. The Na plus is gaining, water's gaining. So there's my reduction. So now out of these two, who's closest to 0? Which one is it? Right? So again, if you think of numbers, you have 0, 1.23, 1.36. 1.23 is closer to 0. You got this one, and then you got this one. This one is closer to 0, right? It would be 0, negative 0.83, and then negative 2.7 further down. So these two are closest to 0. So my E cell would be cathode minus anode. Cathode, negative 0.83 minus anode, 1.23. So that's negative 2.09, you said? Oh, 6. So what do you notice about electrolysis of salt water?
It's never favorable.
It's not favorable, good. What's not involved at all? Salt, which is kind of funny, right? Because you're like, well, what's the deal? What's the point? So, why do you have the salt in there? Why do you have the salt in there? You can't do electrolysis of water on its own. So I can't take the salt out and get the same thing. Why? Right, water doesn't conduct very well at all. It's covalent, it doesn't really have ions. So you usually have to put an acid in it to separate the water. So then you'll get, ooh, here's a question. Okay, so sometimes what they do is they ask this question and then they say, okay, a student collects gas at the anode or a student collects gas at the cathode. And then then it gets kind of crazy. It says, okay, they give you like conditions. How many liters of how many liters of gas are collected here? Or how many liters of gas? So that would be PV equals nRT. So that's kind of part of what we're going to get into, and we're running out of time. But what gas is going to be present at the anode here? Try again. O2. And then hydrogen is going to be here. What are you going to notice? Let's say the student collected them until this thing ran out. How would the levels of gas in the test tubes be at the end of that? So if you had a test tube collecting gas here, test tube collecting gas here, let's say all the conditions are the same, test tube the same size. Think about like the level of the water, because it's going to be displacement, the gas is going to come in. I'm asking, is there going to be the same amount of gas on both sides, different amount? Different, and you can actually figure out exactly how much different. Twice as much hydrogen. Twice as much hydrogen. Why? H2O, right? You have two H's for every one O. See, that's the stuff where it's like they're going to get you if you don't think about it or we don't talk about it, because that's more of a concept than a number, right? All right. Okay, good. You guys feel fairly comfortable with that? Calculating E cell? Good. All right. Last thing for today. All right. Here we go. Write this question down, and I'll do this with you, and then I'm going to give you homework. That's going to hopefully...
We have homework.
Oh, you're going to have more.
Yeah, wait, you already gave us the homework.
Didn't I tell you I was going to give you more?
Yeah.
Thank you. Calculate the number of grams of aluminum produced So I'll do this with you, then I'll tell you what, I'll give you just one of these for Monday and you have the other ones. Calculate the number of grams of aluminum produced in 1 hour. And physics people, this, you're probably a little bit easier for you because this is something I think you do in physics. By electrolysis of molten AlCl3, if the electrical current is 10 amps, which will kill you. I think it's 2 amps. We'll take care of you. Not the voltage, but the amps. That's dangerous. All right. So, calculate number of grams of aluminum produced in 1 hour by electrolysis of molten AlCl if the electrical current is 10. All right. We're using this. I equals Q over T. This is on your equation sheet. Q is charge. That's in coulomb. Capital C. Now, time. Now, in this case, it's hours, but we need to convert that to seconds. This equation has to be seconds because I is our current, which is in amps, is in coulombs per second. That's what amps are. Amps are coulombs per second. So we have to convert the hour. So any of these problems that we're going to do involving this, we got to always convert to seconds, right? So of course I give you one in hours just to be a pain, but you got to convert that to seconds. All right. So now let's write down what's happening, right? So you got AlCl3, and it's liquid. So that's going to be Al plus 3, Cl minus 1. Wait a second. Nope. I knew I was forgetting something. So, and it's actually, wait. Well, I'm going too fast. Yeah, it's Al liquid, sorry. If we're going to decompose, if we're going to break apart aluminum chloride, you're going to get aluminum metal and chlorine gas. But we have to balance this thing here. So this is going to be 2, this is going to be 2, this is going to be 3. Why am I doing this? Because we have to figure out the half reactions. Half of this thing is oxidized, half of this is reduced. So basically what I'm saying is that one of the electrodes, you're going to get chlorine gas, the other one you're going to get aluminum metal. Just like the molten sodium chloride, the one I was explaining over here in the beginning of class. Same concept. All right. So, first of all, we need to figure out how many moles of electrons are being transferred here. So if we split this into 2 half reactions. So over here we have Al plus 3 and Cl minus 1 because that's the ions in the ionic compound. Over here, this is 0 and this is 0 because those are elements. So in the compound, right, there would be charges. But once they gain or lose electrons, so in the cell, you're going to have these ions floating around. They are going to gain or lose electrons, creating these two. So, if we take 2Al plus 3 and it gains 6 electrons, it becomes 2Al0. If we take, I'm just going to make this 6, 2 times 3, 6Cl minus, and they lose 6 electrons, it becomes 3Cl2. So why am I doing this? Because I need to figure out how many moles of electrons are involved with this conversion. So in this, again, another way to, I want to leave that there. Another way to think of this, you have Al plus 3, Cl minus floating around, and you got your anode and your cathode and your battery here. I'm going quick, I know. All right, according to what's happening here, my Al plus 3 is going to gain electrons, go to the cathode. My Cl minus is going to lose and go to the anode. Same thing. Metals always go to the cathode. So they're gaining in that electrolytic cell. It's gaining electrons, plating itself trying to plate itself on the cathode, and then the Cl, you're going to see chlorine bubbles. So, that's why I did this. So we know what's going on, and this is really important. All right. So, here's how we do it. I'm going to run through it real quick. Current is 10. We're solving for Q. We don't know it. Seconds. 1 hour, 60 minutes times 60 seconds, or 60, so 60 times 60, right? Bless you. So 3,600 seconds. 3,600 seconds. So amps times seconds gives us coulombs. Coulombs, we get 3.6 times 10 to the 4th. 3.6 times 10 to the 4th coulomb. So in this problem, they gave me the hours, the time, and they gave me the amps. These types of problems, we always use this equation. So seconds times amps, we get coulombs. Okay. Now the question wants to know how many grams of aluminum, right? Right. Okay. All right. How do we go from coulombs to grams of aluminum? I really don't have time to do it. That's it. That's stupid. All right. So we'll have to pick up with it. I definitely want to finish this Monday. I'm not going to just leave it hanging. So I'll finish this Monday, then we'll start the lab. I only have 1 page of notes left. Guess we have to wait.